Good day everyone, and this is the chapter 3, Networking Media. Networking media. Most networks today use cables to interconnect various devices, employing a variety of signaling techniques. Network cables vary signals among computers, allowing them to communicate with one another. Cables are comparable to a highway system in that each carries payloads from place to place. The payloads on roads are tangible, whereas those on cables consist of sequences of electrical or optical signals. Network cabling are tangible physical media. Regardless of the kind of media in use, data must enter and leave a computer at some point to allow network communication to occur. Cabling and wireless communication are at the heart of network communications because these media supply the network's glue. And there are different kinds of media. Both wired and wireless have limitation. Consider cost and performance when choosing network cabling. Primary cable types. All forms of cabling are similar in that they provide a medium across which network information can travel in the form of physical signal, whether it is a type of electrical transmission or some sequence of light pulses. These are the three most commonly used kinds of network cabling. First is coaxial. Second, twisted pair. Third, fiber optic. Each of these types of cabling comes in a variety of forms, and each has unique design and usage characteristic with associated cost, performance, and installation criteria. The following section begin with a general discussion of cable characteristic, rating scheme, and common elements of information, and then provide salient details for each of the cabling types. General cable characteristic. All cables share certain fundamental characteristics. Studying this characteristic facilitates your understanding of their function and appropriate use. Even though wire-based cables differ radically from fiber optic cables in terms of composition and the types of signals they carry. First is bandwidth rating. Each of the cable can transport only so much data over a given period of time. This is measured in terms of bandwidth, which describe how many bits or bytes of information a cable can carry over a unit of time. Second is maximum segment length. The maximum segment length value falls within a range where signals can be regenerated correctly and retransmit accurately. The third one is maximum number of segments per internetwork. Each type of cable is also subject of latency, which measure the amount of time a signal takes to travel from one end of the cable to another. Fourth is maximum number of devices per segment. Each time a network device is attached to a cable, a phenomenon called insertion loss occurs. Each physical connection adds to the attenuation of signals on a cable segment. Fifth is interference susceptibility. Each type of cable is more or less susceptible to other signals present in the environment, where such interference may be electromagnetic or called electromagnetic interference or EMI, or may result from other broadcast signals called radio frequency interference or RFI. And 7. Connection hardware. Every type of cable has associated connectors that influence the kinds of hardware to which the cable can connect and affect the cost of the resulting network. 8. Cable grade. Building and fire codes both include specific cabling requirements, usually aimed at the combustibility and toxicity of the cladding and insulation that cover most cable. 9. Bend radius. Although some types of cabling are less prone to damage from bending than others, bending many types beyond a prescribed bend radius damage or destroy them. This is particularly true for the most expensive types of cable. For network, this means primarily the fiber optic and heavy-duty coaxial cable must be treated with care. 9th, material cost. This is a good way to compare cables of the same type to one another. The last one is installation cost. Labor and auxiliary equipment can easily cost more than the cable when installing a network. Now that you understand the general characteristic of cabling as well as which characteristic influence selection of a particular cable type, you should appreciate the significance of the strength and weaknesses of the various cabling type discussed in the chapter. Baseband and broadband transmission. Baseband transmission uses the digital encoding scheme at a single fixed frequency where signals take the form of discrete pulses of electricity or light. In the baseband system, the entire bandwidth of the cable is used to transmit a single data signal. Broadband transmission system use a different kind of signaling to transmit information across a cable. Instead of digital pulses, broadband system use analog techniques to encode information across a continuous range of values, rather than using the binary zeros and one that characterize digital data in the baseband environment. These are the two primary approaches to two-way broadband communication. First is mid-split broadband. Uses single cable but divides bandwidth into two channels, each on different frequency. Second is dual cable broadband. Uses two cables connected simultaneously to each computer. The importance of bandwidth. Anyone who is ever spent any time online knows the faster the connection, the better, because accessing information and services is the name of the game in networking, and more. Faster access is clearly better than less. Slower access, it's impossible to overstate the importance of bandwidth when making any kind of network connection. Coaxial cable in local area network installation is obsolete. The majority of coaxial cable in use today is for carrying broadband signals for cable TV or from a home satellite dish to the satellite receiver. The information provided in this section regarding the properties of coax refers to all types of coaxial cabling. Information regarding the use of coaxial cable for a LAN is presented for historical purposes. Keep in mind that this type of cabling should not be used in a new LAN installation. Coaxial cable has single conductor at core, surrounded by insulating layer, braided metal shielding or called braiding, and outer cover or called sheath or jacket. Twisted pair cable, the most basic form of twisted pair or TP. Wiring consists of one or more pairs of insulated strands of copper wire twisted around one another. These twists are important because they cause the magnetic fields that form around a conducting wire to wrap around one another and improve TP's resistance to interference, while also limiting the influence of signals traveling on one wire over another, called crosstalk. There are two primary types of twisted pair cable. First is unshielded twisted pair or UTP, which simply contains one or more pairs of insulated wires within an enclosing insulating sheath. And the second one is shielded twisted pair or STP, which encloses each pair of wires within a foil shield as well as within an enclosing insulating sheath. Fiber optic cable. Fiber optic cable trades electrical pulses for their optical equivalents, which are pulses of light because no electrical signals ever pass through the cable. Fiber optic media is as immune to interference as many medium can get. This also makes fiber optic cables highly secure. They emit no external signals that might be detected, unlike electrical or broadcast media, thereby eliminating the possibility of electronic eavesdropping. In any fiber optic cable, each light conducting core can pass signals in only one direction. This means that most type of fiber cable incorporate two strands, each contained within separate cladding, but such cables may be enclosed within a single sheath or jacket, or maybe two separate cables, each with its own sheath or jacket. In most forms of fiber optic cable, an insulating layer of plastic or glass surrounds the light conducting fibers at the core for reinforcement and to maintain a consistent diameter. Kevlar fibers are used as sheathing because they are extremely strong and resist shearing. Fiber optic cable is not subject to likely forms of electrical interference. Also, fiber optic cable supports extremely high bandwidth. Today, commercial implementation at 10 Gbps are in use. Some testing has shown that glass fibers can carry as much as 200 Gbps. Best of all, the maximum segment length for fiber is best measured in miles or kilometers as shown in the table. Wireless networking in tangible media. Wireless technologies continue to play an increasing role in all kinds of networks. Since 1990, especially the number of wireless options has increased, while the cost of these technologies continues to decrease. As wireless networking becomes more affordable, demand increases, and economies of scale come increasingly into play. Most experts anticipate that wireless networking of all kinds will become more prevalent, if not commonplace, in the years to come. Wireless networks appear most frequently in conjunction with wire networks, often to interconnect physically disjoint LANs or groups of mobile users with stationary servers and resources on a wired LAN. Microsoft calls networks that include both wired and wireless components hybrid networks. The wireless world. Wireless networking has considerable appeal in many circumstances. Related technologies can provide the following capabilities. First, create temporary connection into existing wired networks. Second, establish backup or contingency connectivity for existing wired networks. Third, extend a network span beyond the reach of wire or fiber optic-based cabling, especially within older buildings in which rewiring may be too expensive. Fourth, permit certain users to roam with their machines within certain limits. Each of these capabilities support uses that expand or extend the benefits of networking beyond conventional limits. Although wireless networking is invariably more expensive than cable-based alternatives, sometimes these benefits can more than repay the extra cost involved. The third one is mobile computing. With mobile computing, individual users communicate using a wireless networking medium, such as radio or cellular telephone frequencies, that permit them to move while remaining attached to a network. An easy way to differentiate among these users is to distinguish in-house from carrier-based facilities. Both LAN and extended LAN users or wireless networking involve equipment that an organization owns and controls. However, mobile computing typically involves a third party that supplies the necessary transmission and reception facilities to link the mobile part of a network with the wired part. Most often, the company that provides such services is a communication carrier that offers wireless communication for data as well as voice to its customer. Wireless LAN application. The wireless components of most LANs behave like their wired counterparts except for the media and the related hardware involved. The operational principles are much the same. It's still necessary to attach a network interface of some kind to a computer, but the interface attaches to an antenna and an emitter rather than to a cable. Users can still access the network just as if cable connects them to it. Transceiver or an access point that translates between the wired and wireless networks. This access point broadcasts messages in wireless format that must be directed to wireless users and also relays messages sent by wireless users to resources or users on the wired side of its connection. An access point device includes an antenna and transmitter to send and receive messages wireless traffic, but also connects to the wired side of the network. Some wireless LANs are used small individual transceivers, which may be wall-mounted or freestanding to attach individual computers or device to a wired network. Spectrum is measured in terms of the frequency of the waveforms used for communication, measured in cycles per second, usually expressed as hertz, in honor of Heinrich Hertz, one of the inventors of the radio. Frequency affects amount and speed of data transmission. Lower frequency transmission are slower but carry data over longer distances. Higher frequency transmission are faster but carry data over shorter distances. Middle part of the electromagnetic spectrum is commonly divided into several named frequency ranges or bands. These are the most commonly used frequencies for wireless data communication. Radio, 10 kHz to 1 GHz. Second is microwave, 1 GHz to 500 GHz. Third is infrared, 500 GHz to 1 THz. The important principles to remember about a broadcast medium are those which focus on the inverse relationship between frequency and distance and the direct relationship between frequency and data transfer rate and bandwidth. Wireless LANs make use of four primary technologies for transmitting and receiving data. First is infrared. Infrared wireless networks use infrared light beams to send signals between pairs of devices. These devices typically generate reasonably strong signals to prevent interference from light sources present in most office environments. Infrared works well for LAN application because of its high bandwidth, which makes 10 to 100 Mbps transmission rates easily to deliver. These are the four primary kinds of infrared LANs include. First is line of sight network, require an unobstructed view or a clear line of sight between the transmitter and receiver. Second is reflective wireless networks, broadcast signals from optical transceiver near individual devices to a central hub, which then forwards to a signal to their intended recipients. Third is scatter infrared networks, bounce transmission of walls and ceiling to delivery signals from sender to receiver. And the last one is broadband optical telepoint networks, provide broadband services. This technology offers high speed and wide bandwidth, can handle high-end multimedia traffic, and matches of the capabilities of most modern wired networks. And the second is laser-based LAN technologies. Laser-based transmission also require a clear line of sight between sender and receiver. Any solid object or person blocking a beam blocks data transmission to protect humans from injury and to avoid excess radiation. Laser-based LAN devices are subject to many of the same limitations as infrared, but are not as subject to interference from visible light sources. And the third is narrowband, single-frequency radio LAN technologies. Narrowband radio or single-frequency radio LANs use low-powered, two-way radio communications, much like those used in taxicabs, police communication, and other private radio system. Receiver and transmitter must be tuned to the same specific frequency to handle incoming and outgoing data. Unlike light-based communications, such as infrared or laser, narrowband radio requires no line of sight between sender and receiver, as long as both parties stay within the broadcast range of these devices, typically a maximum range of approximately 70 meters. The last one is spread spectrum LAN technologies. Spread spectrum radio addresses several weaknesses of single-frequency communications, whether high or low power. Rather than using a single frequency, spread spectrum uses multiple frequencies simultaneously, thereby providing reliability and reducing susceptibility to interference. Also, using multiple frequencies makes eavesdropping more difficult because of how individual frequencies are used together for spread spectrum communications. There are two main kinds of spread spectrum communication are called frequency hopping and direct sequence modulation. Frequency hopping switches data among multiple frequencies at regular intervals. Transmitter and receiver must be tightly synchronized to keep communication ongoing, and direct sequence modulation breaks data into fixed-size segments called chips and transmit the data on several different frequencies at the same time. The receiving equipment knows what frequencies to monitor and understand how to reassemble the arriving chips into properly arranged sequence of data. 802.11 Wireless Networking. The 802.11 wireless networking standard, also referred to as Wi-Fi, which was completed in 1997, has been in continual development. With it, manufacturers of wireless networking devices have brought an expensive, reliable wireless LANs to homes and businesses. Wireless extended LAN technologies. Certain kinds of wireless networking equipment extend LANs beyond their normal cable-based distance limitation or provide connectivity across areas where cables are not allowed to traverse. For instance, wireless bridge can connect networks up to 3 miles apart using line of sight or broadcast transmission. Upfront expense may be 10 times higher but no monthly carrier service charge. Longer-range wireless bridge work of distance up to 25 miles using spread spectrum transmissions. Wireless MAN, the 802.16a standard. One of the latest wireless standards, the 802.16a, known as WiMAX or Worldwide Interoperability for Microwave Access Standard, promises wireless broadband to outlying and rural areas where last-mile wired connections are too expensive or impractical due to rough terrain. WiMAX delivers up to 70 Mbps of bandwidth at distance of up to 30 miles. And the next is microwave networking technologies. Microwave systems deliver higher transmission rates than do the radio-based system, but because the frequencies are so high, transmitters and receivers must share a common, clear line of sight. Microwave communications usually require FCC approval and licensing and also are more expensive than do radio systems. There are two kinds of microwave system. First is terrestrial, second is satellite. Terrestrial microwave system are use tight beam, high-frequency signals to link sender and receiver. By using relay towers, microwave system can extend a signal across continental scale distances. And satellite microwave systems send and receive data from geosynchronous satellites that maintain fixed position in the sky. This is how television signals and some long-distance telephone signals travel from one side to the world to another. The sender beams the signal to a satellite visible on the horizon, and the satellite relays the signal to one or more satellites until it comes onto the receiver's horizon. And the last topic is other wireless networking technologies. Because it is so desirable to break the wire tether that anchors user to most networks, wireless technologies continue to evolve and expand, yet simultaneously grow cheaper and significantly faster. We have discussed the IEEE's 802.11b wireless networking standard, along with its higher speed enhancement. This standard promises to continue evolving, making wireless LANs commonplace in homes and in corporate environments. Metricom Incorporation, a wireless service provider based in Los Gatos, now offers cellular pocket radio networking in 3 areas in the United States. First, the San Francisco Bay Area. Second, Washington, D.C. And the last, the Seattle, where users in the these metropolitan areas can carry laptops anywhere within the carriage area. Establish a 2 Mbps connection at will. Cellular Digital Packet Data or CDPD connections at 19.2 kbps are already available in most major U.S. metropolitan areas. CDP technology is being used in handheld and palm-top PDAs for wireless internet and email access, further expanding the capabilities of these devices.